With the last session for today, and I'm happy to be chairing this session, which will have 2 talks and then a discussion session, which I hope it will be lively and it will have a lot of interesting discussion about what we've seen today and the next research in this field. So the first speaker is Richard Parker from the MRC Integrative Epidemiology unit in Bristol. And his talk will be about modeling risk factors for within individual variability, a mixed effect beta-binomial model applied to cognitive function in older people on the ELSA dataset. Thank you.
Thank you. Yeah, I just want to apologize for the length of that title. I'm not going to repeat it because Marco's obviously very kindly just read the whole thing out. So yeah, certainly the least snappy of the titles of the day. I'm Richard Parker, I'm based in Bristol. This is a talk about some work I did with Jessica here in Cambridge and Graciela when she was based in Cambridge as well, along with Kate Tilling, who's my boss, basically based in Bristol. So I've got too many slides. I'm going to go through some of them really quite quickly because they're just establishing context, but you know a lot about the context of these sorts of models anyway. So it's not just I've had too much coffee and too much biscuits if I'm going too fast through my slides, although I probably have had both of those things. So cognition in older age, obviously it's very important to understand it for all sorts of reasons, quality of life, so on. We have an increasingly aging population. Long-standing interest in investigating the mean trajectory of repeatedly measured outcomes, including cognitive functioning. So you've got some differences in mean cognitive performance, but interest also growing in within individual variability, perhaps as an indicator of something else going on in someone, the neuroanatomy, so on, or a predictor of future outcomes. Actually, people differ in how variable they are around some kind of fitted mean. To explore those factors, factors associated within individual variability, one approach, common approach, fairly intuitive approach is to derive a summary statistic for each person independently, but we've sort of explored some of the drawbacks of that in a number of the talks today and in the workshop yesterday, if you attended it, that it typically dispenses information about the error associated with each of those estimates. Like there's many more measures for person B here than person A, but that's typically dispensed with. And the analytical opportunities are not always very flexible. So these are sort of person-level summary statistics. The outcome that we were dealing with is a word recall test. So it's a test of declarative episodic memory. It's constructed from this kind of sequence of events. So 10 words are presented orally to someone. They're asked immediately to recall as many of those as possible. So that's obviously a score out of 10. They do something else for 5 minutes, other tests, and they come back and they say, please remind me what those 10 words were again. And so you get a score of 20. So one thing you'll notice about that is that it's bounded, it's discrete, it's sort of integer values from 0 to 20. And that introduces a possible problem, as I think was maybe touched on one of the questions in the last talk as well, in that we have a sort of floor and a ceiling. So our floor is 0, our ceiling is 20. And so if someone tends to score consistently low, they're going to be less a variable, possibly as an artifact of the instrument, as opposed to them truly being less variable in their memory across time. And similarly, if someone tends to score quite high, quite well on the test, someone scoring in the middle, they've kind of almost got more room to vary on the scale. With these particular data, we thought, well, that's potentially a problem, but in actuality, is it? So we did a few things, one of which was just to derive a plot like this. It's just a really simple plot of standard deviations that we've got for each person on the y-axis, and then their mean score on the x-axis. And people who kind of score middling on average tend to have a higher standard deviation. So that got us thinking maybe that's going to be an issue here. We need to take some care with that when modeling within individual variability in this outcome. So to address these issues, we proposed and applied a mixed effects location scale MELS, what we called MELS, a beta-binomial model. So that bit, the MELS bit, as you're probably aware, that's typically a Gaussian model with a continuous outcome. But here, it might be prone to bias in its estimation of within individual variability due to floor ceiling effects. So Graciela, who I was working with, had done some work comparing different modeling approaches to a bounded outcome really very similar to this, and had found on that occasion that a beta-binomial model fared best. So we thought we'd have a look at that and see if we can develop it for our needs. So that's the MELS bit. The beta-binomial bit, in the beta-binomial model, each observed value of the outcome, so each count out of 20, is assumed to result from trials with an underlying average probability of success. But you don't model those individual probabilities, you model the distribution from which those probabilities are sampled, and you essentially model the shape of that distribution. It's a beta distribution. And there are a number of ways to parameterize this kind of model. The way that we did it was possibly a little bit more readily interpretable in that we've got two parameters. And there's a graphical illustration in the next slide, which probably help explain a bit more, but there's an average per trial probability parameter, which we think is according akin to the location in a kind of MELS terminology. And there's also a dispersion parameter, which we've called theta. It's one of those parameters that has all sorts of different names like pi, kappa, and so on, which is a dispersion or a shape parameter or a variance parameter. So let me just illustrate some example values of those two parameters. So in the column in the middle, those three pretend people or instances have their average probability is at the average of, is at 0.5. However, as we go down the rows, this value for theta, it decreases. And so, which essentially means that they're becoming the distribution of probabilities from which is sampled their sort of probability of success in their trials comes from an increasingly dispersed distribution. So basically, you can see by manipulating this kind of location parameter and this dispersal parameter, you can shift this beta distribution of probabilities around to make it more or less variable, more or less successful, I suppose, on average. And as in a kind of a regular, if you like, mixed effects location scale model, you can, or at least we did, make each of these a function of fixed and random effects. So the resulting, I'm just going to do a time check about halfway through. So the resulting model that we fitted looks like this. So we've got our n, which is 20, that's the denominator. We've got our p, our sort of location parameter, and our dispersal parameter. We model a log function of it. And we've got random effects for the intercept and slope for the location, and a random intercept for scale. And those random effects are allowed to freely co-vary. So we applied this to the English longitudinal study of aging, ongoing longitudinal panel study, designed to be sort of representative of people over 50 years of age, but we limited it to people 65 years or older. We had about just under 10,000 people, and up to 7 measures per person. So just over 4,000 had 4 or more measures, for example. So quickly running through our results. So this is the first 2 slides are the results of the fixed effects for that location parameter. So we found that people, so we fitted a restricted cubic spline. People tend to get less good at older ages at recording words. It's not very surprising, and certainly this would match. And this slightly steeper slope with age matches with previous evidence as well. These are the other fixed effects that we looked at with regard to that location parameter. So for example, again, not surprising, people with higher educational level tend to do better. People with difficulties with activities of daily living do worse. And we had this other kind of very heterogeneous category, which was if the interviewer had recorded sort of anything that might have upset or affected the test results, like hearing issues, tiredness, someone walking into the room and so on. And as you might expect, that had a big effect. Looking at that other parameter, and you notice this goes in a counterintuitive fashion. So lower values of it mean greater dispersion or within individual variability as we're characterizing it. So again, people with higher education tend to have lower within individual variability. People with more difficulties with activities of daily living have more variability, and even more so if there's any of these issues sort of reported. Looking at the relationship between the random effects, for the location effects, it kind of describes sort of fanning out pattern across time. So people with a higher intercept at mean age had a sort of a shallower slope, which makes some sense as a sort of face validity. People with that higher intercept for the location also tend to have lower within individual variability. And people with slopes that decline less steeply also tend to have lower within individual variability. In case you're interested, we estimated these models via BRMS in R. We defined a custom response distribution, although Paul Berkner, the package developer, had actually done all the hard work here. He presented this in one of his vignettes, which is very useful in how to do that. We've got further details in a paper that was published earlier this year if you're interested. Earlier on in our kind of analytical process, we did actually think maybe we can get away with fitting like a regular mixed effects location scale model, like a so-called Gaussian one, I suppose. But we found it was what led us on to the beta-binomial is it was having there's some quite curious, it was quite unstable, particularly with regard to the effect of age on within individual variability. It was very sensitive to how we parameterized it. And we were not very confident that I was actually doing a good job of estimating the true association between age and within individual variability. So that's why we turned to the beta-binomial model. But just a couple of caveats at the bottom there. They are more challenging to estimate. One of the reviewers suggested also supplying the results for each of those constituent tests, those sort of 10 words and then 10 words. And I thought, great idea, tried to fit the models. One of them fitted, the other one like fell down spectacularly. So it just really gave me a flavor of the fact that they are a bit trickier. And the within individual variability effect is not on a scale that's as easily interpretable. And there are other approaches too. So one of which is actually something that John Hedeker and colleagues suggested in one of his software packages, is in the Gaussian model to allow the within individual variability to depend on a quadratic function of the random intercept. That probably just sounds like a load of words that I've just said, but in brief, that would kind of look like this. This would be a sort of standard mixed effect location scale model, parameterize it in a different way, essentially saying I'm not going to allow the random within individual variability effect to co-vary with the random location effects. Instead, I'm going to stick them in as predictors for the function for the within individual variability. And that allows me to express those, for example, as a quadratic function, and hence maybe modeling this kind of situation. So that was another approach we thought about, but again, it didn't seem to really, it didn't seem to perform particularly well in this particular instance. I just thought I'd finish with a couple of kind of more wider thoughts. First of which is the time frame over which we were analyzing stuff was so-called visit to visit. So really quite sparse data for for this kind of analysis, measurements they made every 2 years or so. So here, obviously, within individual variability could be the result of things happening over the short term, also things happening over the longer term, and perhaps ideally one might have a data set of sort of repeated bursts of measurement over time to sort of distinguish short-term and long-term within individual variability. Again, this was touched on in the first talk of the day. There's a kind of, it's a moot question as to what you put in the model for the location, because effectively with these sorts of models, you're kind of assuming everything that isn't catered for in the model for the location is within individual variability of interest. And I don't think there's any kind of right or wrong answer at all with this. I think it's just a question of, it's as much a scientific question as anything else. I guess just being explicit and acknowledging your limitations. And then finally, this is very final question, final slide. I've argued this is an instrument issue, this floor-ceiling effects, and perhaps it is in this situation, but there might be other phenomena you try to measure whereby maybe it's truly a biological issue, like perhaps there are some phenomena whereby you can only go so high on it, or you can only go so low on it. And it is the case that people who kind of consistently have low scores are just less variable. And that's probably quite a difficult to unpick those two possibilities. They are some references, and yeah, move that back. Any questions would be great.